Okay. Okay, great. So I don't know if among you, if all of you have read the paper or not. So I can okay, we can switch to this stage. Okay. So the paper is from the Google Brain team and Google Research team, and it came out in 2017, presenting a new and different model called the transformer. From what people were using at that time. So at that time, it was bi-directional LSTMs, and we're gonna talk about them just in a moment. I will explain what are the RNNs in general and what are the bi-directional LSTM that were used at that time, that were the state of the art at that time, and why transformer has made such a big influence in the NLP research. So they did really well in a variety of tasks, especially the translation with the transformer. So I think it's an important paper to know about, as it is part of the foundation of important models that are nowadays state of the art. For example, ExcelNet. ExcelNet is really based on transformer Excel. So we need to understand what are the transformer and how the model is built, so that we can understand some more advanced models that are used nowadays. So an important remark, this paper is not the first one to talk about attention. They just, in this paper, they present a model where they got rid of all the LSTM, all the recurrence, and the only thing they kept is the attention mechanism. So we're going to talk about the attention mechanism and what it is in depth in this paper. Okay. So Mohammed Habi said bidirectional LSTM with attention was the state of the art before this paper. Yes. Okay. So if you want to talk, just activate your mic and then talk directly, so that I can, because I'm switching the tab, so I'm not seeing the chat in real time. So if you want to talk, just activate your mic and talk directly. There's no problem with that. Okay. There were quite big words in the abstract. So if you read the abstract, it's starting with the dominant sequence transduction models. Okay, so the sequence transduction models are the sec-to-sec models. And basically, these are the best models for translation, for example. And we're going to describe them in a moment. So just put that in your head somewhere, that sequence transduction models are the sec-to-sec models that we're going to talk about in a moment. So basically, in the abstract, they are saying that sequence transduction models or sec-to-sec models are the state of the art in translation tasks, etc. And they are using the attention mechanism, but the model they are proposing is a new and simpler model called the transformer, which only uses the attention model, and which got rid of all the recurrence and convolutions entirely. So the interesting thing is that they achieves 28.4 in blue. And what is blue? Blue is a metric for evaluating machine translation. So I have the Wikipedia page here. So tell me if I switched the tab correctly and you're seeing the Wikipedia page of the blue metric. Okay, let me know if you're seeing it or not. Okay, great. So basically, the blue metric, how it evaluates the sentences. So you have the candidate sentence you have in the first table here. You have the candidate sentence, which is the sentence that is given by by the model, and then you have some references. So for example, person A gives this translation for this sentence and person B gives another translation, because when we translate, like, we can translate any sentence in many forms. So we can have like many translations for one sentence. So basically, what they are counting, what the blue metric counts, the number of times the word in the candidate sentence appears in the references. So, for example, here we have the, and we're trying to see how many times it appears in the reference 1 and reference 2. And they take the maximum numbers of time. So for example, here in reference 1, we are seeing the cat is on the mat, so 2 times the. And in the reference 2, we're seeing there is a cat on the mat, so we have just 1 the. So we have like the maximum number of times is 2 times, and we have 2 divided by 7, which is the length of the sentence. So basically, this is what blue is, and it is like a controversial metric for translation. I think it's worth discussing this metric because there is no guarantee that an improved in blue score is an indication of the improved of translation. Why? Because we're using just 2 or a number of references, and we can translate a sentence in many forms. Okay. So just wanted to.
I can add.
Yes.
Here we are just counting. We're just counting the words that appears in the references. We're not. We don't add the positions.
Yes.
This is the weak thing in blue score, because the same words in different positions may not mean the same thing. That's the problem with blue score.
Yes, exactly. So I know that it is like a really controversial metric for translation, and even if they use it in this paper, we can say that Transformer has changed the way we're looking at models right now, and it's an important paper, even if they are using like blue metric to make the state of the art results they are displaying. Okay. So we're here. Okay, so I'm sharing now the presentation, and I want to go. Okay, so of course this is an original paper, as they are describing a new model, a new transformer simple model for NLP and others and other tasks. So we're gonna like follow this plan for this presentation, and if you want to incorporate more discussions, you're welcome to do it at any time. So first, we're going to talk about the recurrent neural networks and the attention mechanism, talking about the sec-to-sec models, etc. And then we're going to briefly describe what are the bidirectional RNNs, and then go into the details of the paper, describing what is the transformer architecture, the general overview, what is the multi-headed attention layer used in this paper. And I think we're going to stop here for today. If we got advanced in more details, we can talk about the position-wise feed-forward networks, the positional encoding, and then talk about how they did the training and some of the results. So I believe we can stop at B to give a great explanation of what's happening in the paper. Okay. So first, the recurrent neural network. As we said in the first article we read, recurrent neural networks are used for sequence data. And sequence data are text, speech. You can give me a lot of example of sequence data. I believe you know what are these types of data. So, okay. So if you have like a sentence and we want to translate it, or we want to make a feed forward in an RNN layer. So the recurrent neural network, the basic idea of the recurrent neural network is that the layer doesn't have, or the node doesn't have only the input, but have the input and the previous output of, but have the input and the previous output of the previous node. So if we have a sentence, for example, I have a dog, the first thing to do is to embed is to transform the words in this sentence into vectors. Why? Because we cannot deal with letters, we cannot deal with words, but we can deal with vectors and numbers pretty well. So first, we transform them into embeddings. The idea of the embeddings is that we must have some sort of pretty embedding, so that we can like have, for example, the distance between man and king is the same distance between a woman and a queen. So we can have like some sort of manipulation on the words using that embedding. So the first thing to do when dealing with sentences, when dealing with words, we have like some sort of transformation, so that each word is transformed into a vector. So here we have like I, this vector, have this vector A, and then dog, this vector. Okay, so this is the first step. Once we have the embeddings, we give them as inputs to each node of the recurrent neural network layer. So here is the layer. This is one layer. These 4 nodes are one layer. So the first node will apply a certain activation function or a certain block. For example, we've seen last week the LSTM block. So we can like have here multiple activation functions that will either forget something or add something to the context, etc. So here we can have like a simple, just one activation function. And this is the vanilla RNN, where we have just one tangent activation, tangent activation function. So here we can have like an activation function, and it will be applied to the embedding of the word, and we can get the output. The output is h of t. So each h of t is the output of each node. So basically, this is the recurrent neural network. We have a node which with two inputs: the actual input, which is the word embedding, and the previous output of the previous node. Okay. So do you have any question regarding this recurrent neural networks? Or do you have any additional information I didn't give, or something to explain more of, or you want to explain it in another way? Feel free to talk if you want to. Or you can tell me to go ahead so that I can understand that everything is clear here. Okay, it's clear, I think. Okay. Okay, for me, everything is clear. Okay, perfect. Okay, so this is the recurrent neural networks. And then let's talk about the sec-to-sec model. The sec-to-sec model, imagine that we're going to use it in order to have like a translation of the sentence, I have a dog. So I have a dog. We said that we need to make a transformation to get the embeddings, and then the sec-to-sec model is divided into 2 blocks. We have the encoder and the decoder. The encoder will apply a bunch of these layers, the recurrent layers, and we'll apply a bunch of these layers, and we'll get a certain vector. So, for example, we will have this I. It will give us H1, and then have H2, and then A HT, and then dog H4. Let's call it H4. And then H4 will be given to the decoder. So the last hidden state will be given to the decoder, and the decoder will apply a series of layers to get the translation, which is لدي كلب. Okay. So basically, this is the sequence-to-sequence model. We have two blocks. We have the encoder and the decoder. The encoder will apply a bunch of layers, trying to encode the values of the word embeddings, and then give some context to the decoder, which will try to decode it into another, for example, another language. Okay. Feel free to interrupt me at any time if you didn't understand something. Okay, now we incorporate the attention mechanism into the sec-to-sec model. Okay, the problem with this sec-to-sec model is that it doesn't make long distance relations between the words. For example, or it doesn't make any any relation between the previous words. For example, if I have like a sentence, my friend have a dog, his name is Nami, and he is here, here, I'm referring to the dog and not to my friend. So how will the model learn about this reference that he will be referred to the dog and not the friend? So here we need some sort of attention, some sort of reminder that constantly, okay, you need to remind yourself about the other words that you met previously, etc. So the difference between the sec-to-sec without attention mechanism and the sec-to-sec with the attention mechanism is that the encoder, when we're doing this feed forward and we're getting the HT values, will not only give to the decoder the H4, as we said before, and will give the whole H1, H2, H3, and H4 to the decoder. So it will give all the values of the hidden states to the decoder. And the decoder will apply some different operations, which are the attention layers, so that it can notice that, for example, dog, he refers to dog here and not to friend. So I will just show you, okay, here. Okay, so here is the Jalamar blog. It's really the best blog in terms of describing some NLP models like the sec-to-sec, the attention mechanism, BERT, and transformer also. So it's really great. I do need to check it out if you reading a paper is much is harder than reading a blog post like this one, especially with GIFs and animation, etc. So here is an animation. So here we're trying to translate "Je suis étudiant" in English. So I am a student. So for each word, "Je suis étudiant," the encoder will create a hidden state. So we have hidden state 1, hidden state 2, and hidden state 3. And then the 3 hidden states will be given to the decoder. And the decoder will give some values, some importance a value that will describe the importance of the hidden state for each step. So for example, for the first step, the most important hidden state will be the first one, and he will translate je to I. And then for the second word, the most important hidden state will be the second one, and he will translate suis to I am. And then the third word, the important hidden state are the second and the third. And he will give us a, and then student, the most important hidden state will be the third. So this is basically to have an idea of what the attention is. So it gives importance to the words while maintaining all the hidden states. So I have all the hidden states, and I know that the most important one is the hidden state, the first hidden state, but I have all the other ones as well. So I'm not like only seeing the hidden state, the last hidden state to have the whole translation. Okay, tell me if you understand the attention mechanism, or do you have any questions or additional information? Okay, in the paper, just give me a second. In the paper, okay, here in the background, they are talking about the self-attention, and they said it has been used successfully in a variety of tasks, including reading comprehension, abstractive summarization, textual entailment, and learning task-independent sentence representation. So I wanted to give you an example on each of these tasks. So I found this quite interesting application. So, okay. Okay, are you like looking at LN NLP? Yes, okay, great. So for reading comprehension, this is a great application to test different tasks of NLP. So for reading comprehensions, it means that you give the machine a text, and then you give it questions about this text, and the machine will answer according to her reading comprehension of the text. So for example, here I'm giving it a passage. I am in the room doing a presentation about the article I read last week. The article is called "Attention is All You Need." And then I question the machine and tell it what is the name of the article I read. And if I run this, I get the answer, "Attention is all you need," which is quite interesting as a task. Okay, another task they mention is textual entailment. Textual entailment, for example, we can use an example here. Okay. The idea of textual entailment, you have two sentences. You give the machine two sentences, and it is testing if the sentences A and B, and it is testing if A imply B. So it is testing if A imply B. So we have here a large gray elephant walked beside a herd of zebras. And then we have the hypothesis. We have the second sentence, which is the elephant was lost. And here we are trying to see if A implies B or not. So if we run it, okay, it is somewhat likely that there is no correlation between the premise and the hypothesis. Maybe you can try a different example. So if you help the needy, God will reward you. Giving money to the poor has good consequences. So this is entailment. Like this is a clear, very likely that the premise entails the hypothesis. Okay, so these are examples of the tasks that are presented in the paper, and abstractive summarization is the summarization of a text. Okay. So yeah, I think if you don't have any question, we can go and explain what are the bidirectional LSTM. Do you have any question? I don't. Okay. Okay, so maybe someone can explain to us what are the bidirectional LSTMs. I think that the attention is clear, so we don't need to explain what are the bidirectional LSTMs with attention. Sorry. Mohammed, you mentioned them. You mentioned them at the beginning of the meeting. ما نعرفش نشرح. No, this is a discussion. Come on.
Okay, so the problem with the recurrent neural networks that you described was that what the recurrent we look just to the previous element. So here in the bidirectional RNNs or LSTM, we have for each cell, or they are different cells. We have two cells. One is ما بيش كيف نقولها. واحدة رايحة لدروس واحدة رايحة لاغوش. الأولى هذه اللي راهي من تحت هي نفسها اللي كانت في الموديل اللي عطيته هاجر قبيل. تاع الريكورنت نيورال نتورك يقرا يوصلوا دي انفورماسيون من ستيتس اللي كانوا قبله، والاخر يقرا من واش راه جاي في لافراز. بار اكزومبل كون تكون عندنا فراز يكون فيها ضمير ولا نعرف يعيطوا له، بصح هذاك نديروا له ريفيرونس بعدها. في recurrent neural network اللي ماهوش bidirectional ما نقدروش نعرفوا هذا الديبوندونس. المهم ماني خلطتها، قلت لك ما نعرفش نشرح.
نو ماكش تخلطها، انا فهمت.
اوكي شوفيك شما تزيدي.
I think مفهوم. ما بيش إذا كش واحد عنده كيسيون ولا بوزينا. So I think نسرين هذا وين جات نقولوا لها اون غو واش رانا دايرين. اون غو رانا نهضروا على attention is all you need, the paper. And in this paper they presented a new model, which is the transformer. And we didn't start talking about the paper itself, but we started talking about what was there before the paper got published. So we talked about the RNNs, what are the RNNs, and we talked about the attention mechanism, we talked about the sec-to-sec models, and now we're talking about the bidirectional LSTMs. قولوا لي من فضلكم إذا كم حابين نهضر بالعربية قولوا لي نهضر بالعربية normal. باسكو تجيني ويرد نهضر اون انجلي وانتوما راكم حابين نهضر بالعربيه، تما قولوا لي نورمال.
انا برك ما لقيتش كيف نكمل بالانجلي كملتها بعربيه، تبان لي نورمال ما عندهاش بروبليم.
المهم أخيرا انتم قولوا لي. هي المهم أنا من عندي المهم لازم نهضروا إن لونغ كاع نفهموها. تسمى إذا حبيتوا عربية ولا أونجلي ولا فرونسي سي كوم فولي. دونك في باي دايركشنال LSTMs كما قال محمد سيك عندنا كلي عندنا دو لاير في لاير وحده. عندنا لاير راهي تقرا لا فراز من الاخر للاول، وعندنا لاير واحده اخرى راهي تقراها من الاول للاخر، والريزولتا راح يصرالو كونكاتيناسيون. دونك لا كونكاتيناسيون سوا تكون كونكاتيناسيون سوا تكون سام. Ça veut dire que راح يكونوا عندي دي فيكتور y0 y1 y2 هذوما راح يكونوا دي فيكتور راح يخرجوا كما قال لكم من هذا الاول كما خرج هنايا h2 h3 ht etc. دونك راح يخرج عن فيكتور، وانا هذاك لو فيكتور سواء نجمع لي دو سوم تاع لي دو فيكتور اللي يخرجوا لي من اللاير اللي يتقرا من لاكوش لا دغوات ومن اللاير اللي يتقرا من لا دغوات لاكوش، سواء ندير لا سوم سواء ندير لا كونكاتيناسيون. دونك ندير واحد قدام الاخر. Okay, these are bidirectional LSTMs and these were the state-of-the-art model at that time. So اهدري كما تحبين ميلونجي انجليش بالدرجه. اوكي اوكي دونك رانا لاحقين لهنا. دونك ورانا شرحنا سكوسيك RNNs. اذا عندكم questions about RNNs سقسوهم. شرحنا وشنو هما الساك تو ساك و the attention mechanism اللي يدخل داخل الساك تو ساك. وشرحنا وشنو bidirectional LSTMs. كي نقولوا sack to sack with bidirectional LSTMs ça veut dire que هنا لداخل في الانكودر وفي الديكودر راهم لداخل layers تاع bidirectional LSTMs. اوكي وشرحنا وشنو bidirectional LSTMs. قلنا باللي هما اللي كانوا state of the art هذاك الوقت قبل ما يخرج transformer. très bien. دوكا راح ندخلوا في الموديل ونهضروا على transformers ونهضروا على multi-headed attention used by the transformer. Okay. Okay. So I think the most important information that you need to keep in mind is that the transformer got rid of all the recurrence in the model. That means that in the encoder and so the transformer is a sack-to-sack model. So it has the encoder and decoder. But in the encoder and the decoder, we're not going to find layers that contains RNN vanilla or LSTM cells, etc. So we're going to find some other operations, and these operations are really efficient and fast because they don't have this recurrence. So it's really a plus. Okay, so here I'm going to switch to Jalamar blog because I think he gives like a really great high-level look on the transformer. So okay, so I'm gonna like share with you in the chat this one, and okay, so okay, so this blog post is really cool. So first they are like he is like describing what a sack-to-sack model is, and this is not a problem. And then we have like multiple times encoder and then multiple layers of decoder. This is okay. And then we're going to analyze the encoder block in the transformer. Okay, so the encoder block in the transformer contains a self-attention layer and then a feed-forward neural network. So for the feed-forward neural network, I believe you all know what it is. And if you don't know what it is, please let us know by activating your mic or saying it in the chat. So we have two steps in each encoder layer. We have the self-attention and then the feed-forward neural network. And then in the decoder, we have three operations. We have the self-attention. So keep in mind that the transformer is a sec-to-sec model. It contains an encoder and a decoder. The encoder contains multiple layers of this encoder block. So we have 6 times self-attention feed forward, self-attention feed forward, self-attention feed forward, self-attention feed forward, etc. And then we have the decoder. And in the decoder, we have a self-attention and then an encoder decoder attention and then a feed forward. So as we all decided at the beginning of this reading session, each word in a sentence will be transformed into a vector of a certain size, of a fixed size. We choose this fixed size at the beginning. It's generally 512 or 256 or something like this. So here we have je suis étudiant, and then we have like the embedding form of each word, x1, x2, and x3. And we get the self-attention, we go to the self-attention layer, apply the self-attention on each word, and then get Z1, Z2, and Z3, and then a feed forward, and we get the result of the encoder layer. Okay. Okay, so this is basically, okay, so maybe we're gonna talk about the self-attention. It's gonna be better in detail. So in the paper, they are given like, in the paper that they are given the math formulation of the attention layer. It's quite difficult for me to read it in math formulation, and I prefer the illustrated version of Jalamar. So basically what we have is that we have three weight matrix, 3-weight matrices. And when we say weight matrix in deep learning, we mean that all of the information of this matrix will be learned. So at the beginning, it will be random, and then back propagation, etc. And then we're going to learn these weights, okay? So this is a fact that whenever you read weight in deep learning, you will understand that these weights are going to be learned by time, like by the training process. Okay. So here we have the embeddings, and in the attention layer, in the first layer of the encoder, what we're going to do is that we're going to multiply each input by these weight matrices. So we have the W query vector, and then the W key, and then the W value matrix. And then we're going to multiply x1 by WQ, and then x1 by WK, x1 by WV. And then we're going to have the vectors, the query vector, the key vector, and the value vector for each word of the sentence. Okay. Okay, and then these vectors are going to be used so that we can calculate the importance of a word for a certain layer. So what we want to know is that we want to know, as we've seen here, we want to know which hidden state is important to translate for the first word, for example, and then for the second, and then the third, etc. So we want to know the importance of the word when we want to translate, for example, the first word. Okay. For example, here, by applying all the different calculation, we got the first word. For the first word, the softmax is applied at the end to get the probability of, or the importance of that word. So the importance of the first word is 0.88, and the importance of the second word is 0.12. So the importance of the first in translating it is the first word is more important. So this is like this is obvious. Okay, and then we get Z1 and Z2 by multiplying these importance by the value vector. So the value vector is more like what will I have, or what is the result from the first input and from the second input. Okay. I don't really know if I'm explaining it well or not. So if you have any question, please let me know. But if we want to see it like in matrix calculation, so this is like clear, I think. Okay, so let me know if, okay. I think you explain more what does keys, values, a query. I think you explain more what does, what?
I think you should explain more what does keys and values in queries, what does they mean? So for تسمعي فيا؟
سمعت بزاف متقطعت وما سمعتش مليح.
اوكي
دوكا راني نسمع فيك.
قلت لك زعما اكسبليكي واش نديرو بالكيز values and keys queries and values.
اوكي انا كيما راني فاهمه على بالي بلي you can interrupt me اذا راني نقول n'importe quoi واذا على بالك قول. دونك على بالي بلي الفاليوز هما لي فالور اللي راح يعاونونا يعطونا الاوتبوت. دونك بالكويري والكي راح نلقى لا probability اللي راح ندي من هذاك الانبوت، واللي فالور اللي راح نديهم من الفاليوز. دونك الفاليو هي لا بروجيكسيون تاع الوورد.
الفاليو كما قلت هي بروجيكسيون تاع الوورد، وشاك مو عنده كويري وكي. الكي الكويري زعما كي نديرو الكويري 1 كيما نديرو ديك كيو 1 زعما كي نضربوها في عندنا كويري كيو هذه كيو 1 كي نضربوها في الكا 1 زعما كلي رانا درنا كويري من المو الاول للمو الدوزيام هكذا يا اخي.
هي احنا واش راح نديرو؟ راح نضربوا الكويري على لي كيس تاع لي زوطخ مو اللي عندنا في لا فراز. وعلاش؟ باش نعرفوا شحال لا بروبابيليتي اللي راح لو ريزولتا تاع لا ترانسلاسيون يسحق هذاك الاخر، يسحق هذاك لو مو. فوالا دونك انا واش راح ندير؟ راح نملتيبلي باغ اكزومبل كيو 1 بار كا 1 و كا 2 كيما داروا هنايا. فوالا باش يجيبوا لي فالور تاع السوفت ماكس. multiplier Q1 par K1 Q1 par K2 donc راهم multiplier par le keys ومن بعد تيك يجيبوا يابليكيو السوفت ماكس على الريزولتا باش يعرفوا شحال البورسونتاج تاع هذا لو مو راهو يلعب في هذا لو مو. جو عكس هكا.
هذيك هي. والميتريسيز هذوك اللي نضربوهم في الاكس باش نخرجوا كويريز وكيز فاليوز نقراهم ثاني من بعد مع الالغوريثم يقراهم.
فوالا يتعلمهم الالغوريثم. دونك نورمالمون هذه هي السيلف اتنشن. قولوا لنا اذا فهمتوا، اذا ما فهمتوش please let us know. اوكي so نجوزو للملتي-headed self attention. سمحوا لي désolé. اوكي ملتي هادد سيلف اتنشن هي الابليكاسيون ملتيبل تاع the attention from multiple heads. هنا ما بيش ندخلوا البلوس دو ديتاي ولا فيك راهم راحوا نحبسوا هنا باسكو we're supposed نحبسوا في الاتنشن.
تبان لي نكملوا مالتي هاد الاتنشن شنو هي ونحبسوا.
اوكي do you want to describe it ولا
مالتي هاد الاتنشن هي الاتنشن اللي درناها هذوين سيلف اتنشن اللي درنا هذوين بليزيور فوا. وهنا كاين كما راهم دايرين كاين بليزيور ماتريس
كي كويري
كاين بليزيور ماتريس W0 W1 حتى WN كون يكونوا عندنا N هادز وكل هاد عندي
نعم
قلت لك الأذان راه عندك اني نسمع.
ديزولي معليش.
اوكي وين حبس؟ سما هذيك الاتنشن اللي الاتنشن هذيك نابليكيوها بليزيور فوا ومن بعد نكونكاتينيو لو ريزولتا.
وي
نزيدك شما تاع
en gros هاد لو شيما هذايا il l'a très bien décrit. Donc عندنا لا phrase تاعنا نجيبو الامبيدينغز ومن بعد تيكو split into 8 heads. ça veut dire راح يكونوا عندنا plusieurs query matrix key matrix and value matrix. donc راح نملتيبليوهم هادو على شاك input embeddings ومن بعد راح يعطونا لي query key value vectors وبهادو ما نحسبوا كيما واش كنا نديرو نحسبوا زي 0 دونك زي 0 زي 1 اتسيترا. دونك راح نحسبوا لا فالور اللي تخرج لنا من السيلف اتنشن الفيكتور اللي يخرج لنا من السيلف اتنشن ومن بعدك we concatenate the resulting هادوما زي ونملتيبليوهم par une autre matrice اللي يسموها W0 to produce the output of the layer. دونك هاد لي ماتريس هادوما كاع يديك نملتيبليوهم مع بعضهم ان نكونكاتينيوهم مع بعضهم ونملتيبليوهم باغ اون اوتر ماتريس اللي ثانيه راح نتعلموها باش تعطينا لو ريزولتا فينال تاع الصح تاع الاتنشن لاير. هنا واش داروا انيماسيون شابه سيكو داروا باغ لاير شافوا لو مو هذاك اللي من راهو يرجع ايت باغ اكزومبل يعود الى امامه. واش تحب تقول؟
هذا ما كان صح. نقول لك هذه زعما لهنا كاين ريبريزونتا تو هيدز هذا اللي راح اخضر لهنا ايت دارت ريفيرونس للتاير هذه وفي الاخر دارت ريفيرونس كبيره للانيمال.
يس دونك اون غرو هنا واش يورينا بلي كي نديروها بليزيور فوا راح نسيو نكونفيرجيو لا ميم شوز بملتيبل هادز. دونك هكذا باش يعطونا بروبابيليتي بلو كوريكت كو لو كنديرها غير مره. So هنا positional encoding نخلوها لا بروشين فوا نهضروا عليها. And it is an important concept في كاع NLP positional encoding. So I think we're going to stop here. ديجا أذن نروح نصلو. هذيك هي. اوكي يعطيكم الصحة. ميرسي بوكو. السمانة الجاية إن شاء الله.